Good morning. My name is Justin Newton. I work at Remcom, and I will be showing you our updated schematic editor, which now includes optimizations. Specifically, I will be discussing the use of our schematic editor optimizer as it applies to impedance and aperture tuners for mobile device antenna design. Our flagship product is called XFdtd, which is an electromagnetic solver solving Maxwell's equations using the time domain method. XF has a long successful history in the cellular industry. On the left, here we have a typical phone design, and we've pulled apart the layers to show you not only the different layers that are being brought in, but the level of detail we are capturing in the simulation space. On the right, we have a similar example of a automotive radar pulled apart to show you these different levels, including the unique properties of the radome, all being captured in simulation. XF has broad applications for EM simulation, but I will be focusing on how this year we are improving our capabilities for cellular phone design. The smartphone revolution has transformed the cellular phone industry. Increased data demands have led to more frequency bands and techniques such as carrier aggregation. In addition to cellular bands, modern devices must also support Wi-Fi, GPS, and NFC. Complicating this issue, we have limited and shrinking antenna volume, reducing antenna metrics. To overcome this, the industry has moved towards the implementation of impedance and aperture tuners to help recover antenna performance. That brings us to June of 2024, when we released just recently the new version of XF, XF7.11. So what is new to XF this year is that we can now optimize fixed component types and values, as well as the tune codes associated with specific goals and operating modes. We've achieved this by incorporating our particle swarm optimizer directly into our schematic editor. Now, we can optimize on return loss and isolation between ports, and perhaps more importantly, we can optimize on system efficiency. In the following example, the operating modes will be different cellular frequency bands, but I should note operating modes in XF can incorporate much more, such as device states. So in the following slides, I'll be showing you an XF example of a simple DILA antenna structure, which employs both an impedance and aperture tuner. These commercial impedance and aperture tuners use tunable capacitors and switches, which are controlled by tune codes. I will be walking you through a configuration in our schematic editor where the impedance and aperture tuner are implemented as subcircuits in the overall matching circuit for the antenna. So here we have our workflow for the demonstration I'll be showing you. And we're going to start with completing step 0, where essentially we've already designed our antenna and the circuit topology has been determined. From there, step 1 through 5, the following steps will show us how we optimize our configuration. So step 1, we'll use the circuit topology to guide the layout. Step 2, we'll run an XFdtd simulation of the antenna and PCB layout. Step 3 is we'll employ our schematic editor to construct a schematic which includes the XF data, the impedance and aperture tuners, as well as the fixed components. Then we will move over to our circuit element optimizer to optimize the types and values of the fixed components and the tune codes of the tuners. And then lastly, we'll review our optimized results. So here's just a visual image of the antenna. We have it here at the bottom of this substrate attached to the PCB. And we've got our aperture and impedance tuners laid out onto the PCB as well. So here I'm showing the impedance tuner subcircuit. The impedance tuner consists of 5 switches and 2 tunable capacitors, controlled by tune codes which configure the switch positions and the capacitance values. These tune codes are programmable and specific tune codes can be saved. And then shown to the right here, we have the lower level of the subcircuit, which contains the underlying S parameter data. We have the same layout here for our aperture tuner. So here, this is 2 switches which have a common RF input, and on the right we have the lower level of the subcircuit containing the underlying 3-port S parameter data. So step 1 is the layout. So here we have realized the topology for both the tuners as a layout and XF. It is critical that we are capturing the electromagnetic interaction of the pads and traces as well. If this was a product bought from a vendor, they would have specific layouts and best practices to guide this layout step. So here we are showing the DILA antenna with the layout of the impedance tuner and aperture tuner in the XF model. This will give you an idea of the layout with respect to the rest of the structure, all within the XF simulation space. Next, we'll set up our XF simulation. So now it's time to set up the actual simulation parameters. Here we will show all of the ports in the XF model which need to be defined, and they correspond to fixed components as well as our impedance and aperture tuners. In this case, we have 25 ports. Next is we will go over to our schematic editor with those XFdtd results. So once we run the XF simulation, we will get a resulting XF block, which can be used in the schematic editor. So we'll pull that XF block, which contains the results from our simulation for all of those 25 ports, into the schematic editor, and we have that here in the center. Then we will connect to the FDTD block, the aperture and impedance tuners, along with the fixed components to the appropriate ports. And this will define the overall schematic for the entire system. Yet to be determined are tune codes for the tuners and component types and values for the fixed components. Next, we will implement our schematic editor optimizer. And we'll start by defining operating modes. In this slide, we will define our individual operating modes. The specific impedance tuner settings will be optimized for each operating mode, and the fixed components will be optimized for all operating modes. And the aperture tuner will be a priori set for each mode. The operating mode allows you to have multiple states in one schematic, and in this case, each one corresponds to a different cellular band. And you can see that here, cellular band 5, 48, 2, and 13. Next, we will step through and assign goals for the specific frequency ranges of each operating mode of interest. In this case, we are optimizing on system efficiency. Next, we will configure our particle swarm optimizer, which will determine the best tune codes and fixed components to realize our goal for system efficiency with each operating mode. And lastly, we'll review our results. So after the particle swarm has given the optimizations, we can review the results, and here we have the system efficiency for the different bands. We have band 13, band 5, band 2, and then band 48 here on the far right. We also get the tune codes out for our impedance and aperture tuners, and we get the component types and values we saw in our schematic. So finally, as long as the simulation is set up properly, we only have to run one XF simulation. And then we can push back the schematic onto our previously run XF simulation to determine quantities such as envelope correlation coefficients, far field patterns, near field results such as SAR. By use of the superposition principle, these data can be determined from the previously run XF simulation. Thank you. That it concludes this presentation of the optimizations we've implemented in 7.11. Please feel free to reach out to us with questions, or if you'd like to try this feature set out yourself, please contact me and I'll be happy to arrange for your access to the tool and support you with helping you learn how to use these features. Thank you.